Okay, so good day, everyone. So we are now in the next topic, which is the elastic stresses, concrete crack. So here's the concept for that. When the bending moment is sufficiently large to cause the tensile stress in the extreme fibers to be greater than the modulus of rupture, it is assumed that all of the concrete on the tensile side of the beam is cracked. Okay, and must be neglected in the flexure calculation. So it was mentioned already here. The tensile stress is greater than the modulus of rupture, which is Fr. Then on the tensile side, the beam is considered as crack. Now, so as you can see here in the figure, so this is our initial beam. Okay, so the rectangular beam. Then as you notice, so this is the only concrete portion of the beam that is left now, so since due to this condition mentioned here. Okay, so there are some reasons for it as well. The cracking moment of beam is normally quite small compared to the service load moment. Okay, so take note of that. Then thus when the service loads are applied, the bottom of the beam cracks. Okay, so that is one of the reason. Okay, so moment service load is greater than the cracking moment. Okay, so the cracking of the beam does not necessarily mean that the beam is going to fail. Okay, so cracking is not really equal to failure. No, that is only a normal scenario for concrete. No, since the reinforcing bars on the tensile side begin to pick up, the tension caused by the applied moment. On the tensile side of the beam, an assumption of perfect bond is made between the reinforcing bars and the concrete. Okay, so thus the strain in the beam and the steel will be equal at equal distance from the neutral axis. So if the strains in the two materials at a particular point are the same, however, their stresses cannot be the same since they have different modulus of elasticity. So technically, steel and concrete do really have a different modulus of elasticity. So thus, their stresses are in proportion to the ratio of their moduli of elasticity. So take note of this, that the ratio of the steel modulus of the concrete and the uh, concrete modulus is called as modular ratio, or N. N is equal to ES over EC. Okay, so next for the procedure. Okay, so we have two procedures here, or analysis, that we will going to discuss: analysis for singly reinforced beam and analysis for doubly reinforced beam. Okay, so let us discuss first the procedures in analysis for singly reinforced beams. Okay, so here are the steps uh, in order to apply the analysis for singly reinforced beam using transform method. Okay, so first step is replace the steel bars with an equivalent area of fictitious concrete, which is equal to N times AS, which supposedly can resist tension. So the area is referred to as the transform area. Okay, so meaning from the original beam section, so you will have an equivalent. Okay, you will have an equivalent beam section. So since this portion here of the concrete is considered as crack, then the steel bars will resist that one, will pick up the tension, and that this should be converted into N times AS. Okay, and the remaining part of the concrete is this compression portion of the beam. Okay, so this is the concrete portion here. Okay, then uh, for the second step, locate. Okay, so locate the neutral axis, which is assumed to be located at a distance x by equating the first moment of the tensile area to the compression area of the beam cross section about the neutral axis. Okay, so later on we will discuss further what is this x distance in our example. Normally x distance is denoted as this one. Okay, x distance here on the concrete portion or the compression side. Okay, the third one is to calculate the moment of inertia ICR of the transform section. Okay, so this is an equivalent beam section or the transform section. Okay, take note. So transform, that is considered as a transform section as well. Then after getting the ICR, then normally we are tasked to compute the stresses in the concrete and steel using flexure formula. Okay, so we have two, that is for the compression concrete. Okay, the stress is calculated as FC is equal to My over ICR. Then also we have for tensile steel, which is the stress is calculated using Fs over N, which is equal to My over ICR. Okay, so the only difference there is a subscript, and in for steel bar we need to have this denominator of the modular ratio, no, on the stress portion of the formula. Then we also have this one for problems where allowable moments are to be determined. The actual stresses for both concrete and steel should not be exceeded, no, definitely, since we are only tasked to know the allowable moments. Okay, so the allowable stresses, if not given, you will have 0.45 F prime C for concrete, so this is FC. Okay, FC allowable, and 0.6 Fy, which is Fs allowable for steel. Okay, so those are the procedures, so simple procedures, no, for singly reinforced beam. Okay, so let us discuss the first example, which is example 2.3. We are tasked to calculate the bending stresses in the beam using the transform area method given the following properties. So F prime C 21 MPa, given moment which is 95 kilonewton meter, then B is, or the width is 300 mm, the total height H is 500 mm, then we have the effective depth which is 425 mm, and we have AS, which is 3 bars, no, 3 bars in 28 mm diameter. For letter B, we are tasked to determine the allowable resisting moment of the beam if the allowable stresses for concrete is 9.31 MPa and 138 MPa for steel. Okay, so let me draw this one. Okay, so we have example. Okay, so we have example 2.3. Okay, so let me draw the beam, guys. So our beam is this one here. Okay, so we have three bars, 328 mm bars. Then this is 500 mm. Okay, then this is 300 300 mm. Okay, then we have the distance here, the distance which is equal to 425 mm. Okay, so this is our beam section. No, this is our beam section. Okay, then we will have a, okay, so from the question, so we are tasked to get the bending stress using transform area method. Okay, so let us follow first the first procedure. Okay, so for the first procedure, we are tasked to replace the steel bars with the equivalent fictitious uh, concrete. No? So we will have a transform area, or we will have this equivalent beam section here. Okay, so let me draw. Okay, so this is our transform section. So say this is the only concrete concrete that is the remaining, or the remaining concrete. So this is still 300 mm. So say okay, say this is the neutral axis, so we'll just assume that one. Then from the bars, okay, so we have this fictitious concrete area here for the bar, which is equal to n times as. Okay, then with that, so let us proceed to the second step, which is to locate the neutral axis, which is assumed to be located a x distance, no, by equating the first moment of the tensile area to the compression area of the beam cross section about the neutral axis. Okay, so so this is now the x distance that is being mentioned, and this one here, no, from the neutral axis to this portion of the bar, so this is d minus x. Okay, so okay, so in order for us to locate the neutral axis, okay, so first we need to verify if the beam is cracked. Okay, so in here, verify the beam is cracked, no. So let me verify that one. So we have formula that we know already, that MCR is equal to FR IG over YT. Okay, so we have FR, which is equal to 0.62, then times 1.0, since this is a normal weight concrete. Then we have square root of, so we have square root of 21. Okay, then multiply it with IG, which is equal to B, then H cube over 12. Okay, then all over YT. So YT is half, no, half the total depth, which is 500. So YT is 250 mm. Then multiply it with 1000 squared, so that we could get a value of moment, which is in kilonewton meter unit. Okay, so we have MCR, which is equal to 35.515 kilonewton meter, and from the given M is equal to 95 kilonewton meter. So this is the moment applied, no, moment applied in the example. So therefore this is less than MCR is less than MCR is than M, which is 95 kilonewton meter. So therefore the beam is cracked. Okay, so we already verify it now that the beam is cracked. So therefore we are in the right track of computing a stress, the bending stress using transform method. Okay, so next, since it is cracked, then we are now tasked to locate. Okay, so locate NA. Okay, so locate NA. So first is we will have the first moment, as mentioned here. First moment of the tensile area in with respect to the compression area about neutral axis. So we will equate the two. Okay, the first moment of the tension area and the tensile area. Okay, so this is the in order to get the first moment, so we have 300 times x and times x over 2. Now this is for the compression part. Okay, so this is the area. Okay, so area bar x. Okay, so area of this one. Okay, so area of this one, so which is 300 times x, then the bar x, which is the x over 2. Okay, then equate it with the tensile area, which is the NAS. Okay, which is the NAS times d over x. Okay, this one, the NAS then times d over x. Okay, so let us compute first the NAS. Okay, so NAS N. Okay, so N is equal to ES over EC, and this is equal to 200,000 MPa over 4,700 square root of 21. Okay, and n should be in whole number. Okay, so take note that n should be in whole number, and I think this is rounded off to 10. Okay, so n is 10. So therefore this is now 10, then times AS. So since you have diameter, area of the diameter of the bar, which is pi over 4, 28 squared, then times 3. Now since we have 3 bars. Okay, so this is area. Okay, so this is N, and this is AS. Okay, AS. Okay, so area of the bars. Okay, so area of the circle of the bar, then times 3 pieces, no? So 3 pieces of, okay, 3 pieces of bars. Okay, then do not forget the bar x, no, which is this d minus x. Okay, wherein d is equal to 425 then minus x. Okay, so try to calculate that one for you to get the value of x. Okay, so I think x is equal to 175.345 mm. So let me get the value of d over x as well, which is equal to 249.657 mm. Okay, so this is equal to 425 minus x. Okay, so these are the values, no, values for our x and d over x. Okay, so now I think we need to proceed to our next step, which is to calculate the moment of inertia of the crack section or the transform section, which is the ICR. Okay, so for the ICR, okay, for ICR, so we have ICR, this is summation of IX plus AD squared. So I think you're familiar with this one. Now the local moment of inertia plus the transform formula, which is area times d squared. Okay, so let me get first the inertia for the concrete portion or the compression side, which is equal to 300 b x cube over 12. So take note that is came from the this one. Okay, the concrete portion or on the compression side, okay, of the beam. So we have h cube over 12. So definitely we have value for x already, this one here. Then plus area 300 times x, then x over 2 squared. Okay, so we need to transfer that one since the local centroid of the concrete is in here, no, and the neutral axis in this one, no, or this point here is the global centroid, no, for the section. So we need to transfer the inertia of the concrete portion. Okay, so then plus, so we are already finished with the concrete side or compression side. So we need to add plus the tension side, which is the NAS, then times d squared, no. So we don't have IX for the tension side, no, because that is very little in portion, no. As you can see here, this is a very little in portion. So this is now converted into AD squared. Okay, AD squared. So let me get the value of NAS, guys. Okay, so I think NAS is equal to 18,472.565 mm squared. So please verify if this is really the value for this one here. Okay, for this calculation here. So that is 18,472.565. Okay, so that is area, which is 18,472 point, let me erase this one. It is 18,472.565, then times area d squared rather, 425 minus x squared. Okay, so take note guys that you may still simplify this one. Okay, this equation here. Okay, so that would be simplified into bx cubed over 3. Okay, so just simply add 1 over 12 then plus 1 over 4. Now if you try to simplify this equation here, okay, now this equation here, so that will be equal to bh cubed over 3. Okay, then plus 18,000. So let me rewrite 5, 6, 5, then 4 to 5 minus x squared. Okay, so just simply substitute the value of x. So therefore ICR is equal to 1.69 times 10 raised to 9 mm raised to 4. Okay, so this is our moment of inertia, or moment of inertia of the transform section. Okay, so now we could already calculate the values of the stresses for concrete and steel. Okay, so for concrete, okay, so for concrete, so we have FC, which is equal to mx. Okay, so mx over ICR, wherein the moment is the applied moment, which is in 95, okay, times 10 raised to 6. Okay, so convert that into Newton mm for us to be consistent. Then the value of x, 175.343, and then over ICR, which is 1.69 times 10 raised to 9. So therefore FC is equal to 9.857 MPa. Okay, so this is the stress for concrete. Okay, stress. Okay, concrete stress. Then for steel, stress no lang steel, so we have Fs over N, which is equal to M times D minus X over ICR, which is Fs over N, which is 10, then M is 95 times 10 raised to 6, then D minus X as computed earlier, and that is equal to 249.657. Okay, so 249.657, then all over 1.69 times 10 raised to 9. But therefore Fs is equal to 140, sorry, okay, so we have 140.34 MPa. So that is for our Fs. Okay, so next, that is for letter A. Okay, so this is for letter A. Now let me solve letter B. Okay, so letter B, so we are tasked to determine the allowable resisting moment of the beam, okay, with these given allowable stresses for concrete and steel respectively. Okay, So we have mm, for concrete, okay, we're given FC allowable, that is less than or equal to 9.31 MPa. Okay, so now we have M. Okay, so formula of FC, which is M allowable, which times X, then over ICR should be less than or equal to 9.31 MPa. So we have M allowable, then let me multiply this one with 1000 squared now for us to get a moment later in kilonewton meter now, then times 175.343, then over ICR, which is 1.69 times 10 raised to 9. This is less than or equal to 9.31 MPa. Okay, so therefore M allowable, using the concrete, guys, now using the concrete condition of stress, which is 9.31, this is equal to 89.73 MPa. Okay, then how about if we'll be using the FS allowable, which is less than or equal to 138 MPa. Okay, so we have that formula for Fs now, and we have M allowable, then times D minus X times N, then over ICR. This should be less than or equal to 138 MPa. Okay, so now, so we have M allowable, again multiply it with 1000 squared, then we have this 249.657, that is our D minus X. Then we have our modular ratio, which is 10, and then over ICR, which is 1.69 times 10 raised to 9, less than or equal to 138 MPa. So we have therefore the M allowable, using the allowable stress for steel, which is 138 MPa. So we have 93.42 MPa. Okay, so the question now is that we have two. Okay, so we have two values of allowable resisting moment, okay, for the beam. Okay, so we have get the allowable resisting moment for concrete, and this is for resisting moment for steel, but we have to choose one allowable resisting moment for both conditions, which is compatible for both concrete and steel. Okay, so we have to conclude that therefore the M allowable, okay, for the beam, not for the whole beam. Okay, so we need to choose on the two values. Okay, so we need to choose the lesser value, which is the 89.72 73 rather 73 kilonewton meter. Okay, let me correct this one. This must be in kilonewton meter, as well as this one. Okay, this should be in kilonewton meter. Okay, so therefore the answer is 89.73. Okay, so the explanation for that one is that if you will exceed, no, if you will consider Okay, if you will consider this value, then your beam might fail. Okay, might fail in the compression side, in the concrete side. No? So since the allowable moment for the concrete is only 89.73, no? So if you apply this moment into the steel portion or the tensile or tension side of your beam, then that won't hurt. No, that won't hurt the tension side, since the allowable moment there is 93.42. So you still have allowance of 4 kilonewton meter. Okay, so we get the lesser value for us to ensure that for both compression or for both concrete and steel, uh, both of them are safe, no, when when this moment is applied, no, on the beam, and with the following conditions of Fs allowable, which is 138, and Fc uh, allowable, which is 9.31. Okay, so I hope it's clear already for our first example. Okay, so that is for our first example. So let us proceed to our next example, which is example 2.4. Okay, let's proceed to example 2.4, which is the okay example 2.4. So example 2.4, so we are tasked again to calculate the bending stress on the concrete and reinforcing steel using transform area method. Okay, so with the value of n, which is 9, then the applied moment would be 339 kilonewton meter. No? And with the following properties, so we have width of the web, then width of the flange, then height of the flange, then the D distance, which is the 700 mm. So expect that this is a T beam. This is a T beam, guys. So let me draw this one. So this is T beam. Okay, so this is 125 mm, and this is 1500 mm. This is BF, this is HF, then we have BW, which is 300 mm. Then if we have AS, no AS, so let me put a AS here. So we have AS in this portion. So I think AS is given, which is 628 mm. Then the value of D is equal to 700 mm. Okay, that is for the T beam portion. Okay, so now so first, again, verify if it is cracked, but I assume that this is cracked already, since the applied moment given, which is 339, is very large or massive. Now this is a massive moment, so you may still verify if it is cracked if you wanted to. Okay, so proceeding to our first step, which is to transform this one into a crack section. No? So there are two tendencies for the values of x, guys. Now x might be within the flange. Okay, so meaning your x might be within the flange, within this portion here, or there would be tendencies that your x might be within the web. Okay, so I hope it's clear. So we have tendencies for this one. The x value is within the flange, or your x value might be within the web. Okay, so just assume, no, if you wanted to assume that it is in the flange, then later on the value of x will reveal that one. Okay, if the value of x, no, so if the value of x is less than 125 mm, which is, this is the HF. No, so if x has a greater value of 125, or this is HF, then this is within the flange, right? And this is within the web. Okay, so I hope it's clear now for this in this matter. Okay, so but for now, let me assume, know that the x is within the web. Okay, within the web. So within the web. Okay, so that is in the web. Now this is our assume an. Okay, so and also do not forget the this one, the NAS, NAS. Okay, so this is our NAS. Okay, so say this is our x, this is our x, then this is our d minus x. So this is 15 mm, then this is 125 mm. So definitely this portion here, okay, this portion here has a value of x minus 125 mm. Okay, and this is still 300. Okay, 300 mm. Okay, so let me compute first the value of NAS. No? So NAS is equal to 9, given n is equal to 9 times 6, then times pi over 4 d squared. Okay, so this must be equal to 26,507.19. Okay, mm squared. Okay, so that is our NAS. Okay. So now locate x. Now, so we are tasked to locate x. Okay, so locate x. So again, in order to locate s, then we need to get the first moment of the compression and the tension side and equate the two. Okay, so we have 1,500, then times 125. Okay, then this is 125 or this is x, no? X minus 125 over 2. Okay, so what we're calculating here is this portion, no? Is this portion of the flange, this portion of the flange here. So 1/5 plus 125, then this is a centroid, no? So that is x. So this is I think this is 125 now. 125. Okay, so that one there is 125. Now 125 over 2. Okay, so x minus 125 over 2, then plus 300. This is the web portion, no? So take note, this one here is the flange, no? The flange portion. I hope it's clear. Then 300, then times x minus 125. Now this is x minus 125 here. Okay, x minus 125 okay, x minus 125, then also get the centroid distance, no? So that is x minus 125 over 2. Okay, then equate that one. Okay, so this is the web portion. Okay, the web portion of the beam. Then equate that one to 26,507.19 NAS, then times x or d minus x, so 700 minus x. Okay, so this portion here is the NAS times d minus x. Okay, so the left side portion, or the left side terms are for compression, and the right side terms is for the steel bar. So now so let's calculate the value of x. So I think x there is equal to 141.28 MPa, or mm rather. Now so this is greater than 125 mm, which is the HF, then therefore the assumption is correct. That x, that x is within the web. Okay, within the web or outside the flange. Okay, so I hope it's clear already. Then we are tasked to calculate ICR. So ICR is equal to 1,500 times 125 cube over 12, then plus 1,500, then times 125, then times x minus 125 over 2 squared. Okay, so take note guys that this is for the I think this is for the flange portion, no? So this is the flange portion, guys, no? As you can see in the figure, no? As you can see in the figure. Okay, so we are calculating this portion here, no? This portion here of the beam. Okay, so next is to have the web portion. Okay, the web portion. So you have plus b, and then h. So we have x 141.28, then minus 125 cube per 12, then plus 300 times 141.28 minus 125, then x minus 125 over 2, x minus 125 over 2 squared. Okay, so this is for the web portion of the second term. Okay, so I hope it's clear already. Then plus, do not forget the tension side, which is 26,507.19, then times 700 minus x 141.28 squared. Okay, so I hope ICR is equal to 9.68 times 10 raised to 9 mm raised to 4. Okay, so that is for our ICR. So this is for the this portion here is the flange portion, then this one here is the web portion. Okay, this is for the web portion. Okay, and this one here is for the, and this one here is for the tension side. Okay, this one. Okay, so I hope it was clear already. So therefore we will calculate the stress for concrete and steel. So we have for concrete, okay, so for concrete we have FC is equal to mx over ICR. Now this is equal to 339 times 10 raised to 6, convert it into Newton mm, then times x 141.28, then over 9.68 times 10 raised to 9. Okay, then so therefore FC is equal to 4.95 MPa. Okay, so this is the stress for concrete. Then for steel, okay, for Fs, where Fs is equal to M times D minus X, then do not forget to multiply it with modular ratio, because that is the denominator of Fs in the formula, then ICR. Okay, so we have 339 times 10 raised to 6, then we have 700 minus 141.28, then times 9, value of n, then all over 9.68 times 10 raised to 9. Okay, so therefore Fs is equal to 176.1 MPa. Okay, so that is for the steel, the stress for steel. Okay, so I hope the topic for singly reinforced beam for the transform area method is already clear. So that's all for our topic. So thank you guys for listening and keep safe everyone.